There we go. Let's see, maybe if I can stay on one side, we can pick up the periodic table too. And we're recording. Video settings, fine, audio, good. Okay. All right. Anything stuck in your craw?
A little bit.
What I usually do is, with my other classes, is if nobody comes up with anything, I just start at the beginning, and then something usually clicks.
Yeah.
Then the questions come.
Yeah. Well, you guys start at 1.
Yeah. Usually, unless I see one that really strikes my fancy, I just do the odd ones.
Okay.
So for this first one, we want for the reaction of sodium bromide with chlorine gas. Sodium bromide with chlorine gas, which means chlorine's diatomic, and produces sodium chloride. It's got to be a solid, and this has to be a solid too. And bromine. Bromine is also diatomic, but bromine's a liquid. I mean, that's not important for the question. I'll just put that up there. So, the question is, what are the appropriate half reactions for this one? Well, we need to separate them into oxidation and reduction. So in order to do that, we have to determine the oxidation states, right? So pure elements are always 0. Those are the easy ones, right? The sodium is a alkaline metal. They're always +1. Right? So that means chlorine's going to be 1 minus, bromine's going to be 1 minus. So now we can tell which one's which. What happened to sodium? Nothing. Sodium's a spectator. Bromine went from -1 to 0. So did it gain or lose electrons? It had to lose an electron to go from -1 to 0. 1 electron per bromine. We'll deal with that a little more in a minute. And that means chlorine had to gain an electron. Because you can't have one without the other. Now the question is balancing them. So if bromine lost 1 electron, but we've got 2 bromines over here, that means we have to account for, we have to account for 2 electrons. In order to do that, we need 2 of these. Same thing for chlorine. Chlorine lost 1 electron per chlorine, but there are 2 here, so that means we need 2 there. Okay? So now the oxidation is oil. Oxidation is lost. So we need to do this one. and it lost 2 electrons, so that means they have to be on the product side. And then we went from this bromine to that bromine. Okay, so that's the oxidation. The reduction is going to be gain. Reduction is gain. So we have 2 chlorines, and gain electrons, they have to be on this side. And we went to you know what? Sodium is, okay, let me finish this then. There we go. But we said sodium is a spectator, right? So in order to write the correct reaction without creating mass, right? Because we got a sodium here and none over there, that sodium has to be gone and leave behind that ion. This sodium has to be gone and leave behind that ion. That's the proper oxidation reduction reaction. So the one that satisfies that one looks like 2Br minus, looks like B. B would satisfy that one. So that problem's a little more complicated than it looks like. We had to identify the spectator in order to give you the proper oxidation reduction steps. Okay. Anything come to mind yet?
Number 3.
Number 3, okay. The following reaction occurs in an aqueous acid solution. And iodate ion, nitrogen dioxide. Okay. In the balanced equation, the coefficient of water is. Now, if you've never seen the procedure for balancing one of these equations, you ask yourself, what are they talking about? There's no water there. But we know that we're gonna add water. And the key to knowing whether you're going to add water or not is that oxygens. That means you've got to put water in there. And then the other key is aqueous acid solution. You're going to need protons too. Okay, so we need an oxidation step and a reduction step. We have to decide. This one, of course, is -1 oxidation state. Oxygen is a 2-, so we have 6- total, but we have to hold 1 out for that minus. So that means we only have to balance 5 minuses. So this is 5+. This one's also 2-, 6-. We have to hold 1 out. So we only have to balance a 5- with a 5+ for iodine. Check your copy of the battery lab and see if it matches this one. I may have given you guys the wrong one. They're only minor changes, and I'll call them to your attention if that doesn't match the one you have. Okay, so now we're down here. Oxygen's -2, so that's 4-. We need to balance all 4 of those because this is neutral. So that nitrogen, only 1 nitrogen, has to be 4+. Okay? So-
I didn't print off
You need,
this chapter. Can I get a?
yeah, sure, I have extras. All right. Okay, so now that we've got the oxidation states, we can decide which ones reduced and which ones oxidized. So for oxidation, we need to find out which one lost electrons. Let's see, nitrogen went from 5 plus 4. That's a gain. This one went from -1 to 5 plus. So it had to lose electrons. Right? So how many did it lose? I look at it this way. To go from -1 to 0 is 1 electron. To go from 0 to +5 is 5 more. So there's 6 electrons. So our oxidation is this one to this one. And I'm going to put those values up there. That means the other one has to be the reduction. So NO3 minus goes to NO2. So that gained electrons. We're not going to put the electrons in there yet because we've got to keep things in order. First things we do is balance the non-oxygen, non-hydrogens. So we've got 1 iodine, 1 iodine, 1 nitrogen, 1 nitrogen. That's done. Then you balance the oxygens with water. So we have 3 waters on this side. That means we need 3 oxygens on that side. We need 3 waters on this side to give us 3 oxygens. We've lost an oxygen here, so it's going to show up over here as an oxygen. So we have 3 and 3, we have 3 and 3. Now we balance the hydrogens, as this is in acidic solution. So we've got 6 hydrogens there. That means we need 6 hydrogens here. We have 2 hydrogens there. We need 2 here. Okay. Now we can balance the electrons. All right. From -1 to 5 plus, we had 6 electrons that were lost. So lost electrons show up on the product side. This one gained an electron to go from 5 plus to 4 plus. There's only 1 electron. Now, before we can recombine these into the final equation, we need to balance the electrons. This one has 6 electrons, this one needs 6 electrons. Okay, so if we're going to have 6 NO3 minus plus 6 times 2 is 12 hydrogens plus 6 electrons, and then 6 nitrogen dioxide and 6 water. Okay, so these are the 2 that will be combined. Now, we could go ahead and write the final equation, but to answer the question, what's the coefficient of water? All you need to do is balance the waters, right? So we've got 3 waters on this side and 6 waters on that side. These 3 are going to go and leave us with 3 here. Right? So the answer to the question is 3 waters, which is C. Okay? In the middle of exam, of course, you don't want to spend a lot of time doing unnecessary work, right? So we just deal with the question. Okay. Another one?
Hey, Dr. Boy,
Uh-huh.
the Zoom meeting from the last week when I missed, I guess I thought maybe it was going to be available to see, and checked, and it's not.
No.
It's a Zoom meeting. It's not like you recorded it and I could go back and access it.
Not tried to record it, and it failed.
Okay.
Yeah.
That's okay. It'll be all right. I went on a few times. I was like, why can't I find this? Why can't I get it? And then
I thought I had sent an email explaining that problem. Did I?
Maybe.
I didn't. Okay.
But that's okay.
Let me take a quick check here. Let me pause this.
So yeah,
All right. Now we're back in business. Okay. Is there another one?
number 11.
Number 11. Okay.
It's like galvanic cell. What is that?
Battery.
Just
It's another name for a battery.
okay.
Yeah.
I mean, I was kind of guessing that based on the rest of the question, but.
Yeah.
Be clear.
It's a way of harnessing the transfer of electrons during an oxidation reduction reaction. Okay, galvanic cell with this reaction dichromate. This one.
So this is basically all the study of the effect of using an electric current to transfer charge
No,
in reactions,
the
like push them forward one way or another?
no,
No.
that's a subcategory.
Okay.
The redox reactions are defined by transfer of electrons. If the reaction is spontaneous, as you set it up, then you can construct a galvanic cell and access those electrons as they move.
Hmm.
That's a spontaneous reaction. If you want to drive the reaction in reverse, then you provide an external direct current opposing the spontaneous direction, and you run the reaction in reverse. Okay, that's an electrolytic cell. Okay, so calculate the voltage of the standard cell carrying out this reaction. Right, in order to do that, we need to know which one's the cathode and which one's the anode. And just as a review, what happens at the cathode? Reduction. And the anode then would be oxidation. Okay, so these are easy. 2 plus, 3 plus, 3 plus, 2 minus. see. We don't actually have to balance this equation like we would normally do. We just need to identify which one's the cathode and which one's the anode. So which one's being reduced? Well, let's see. Oxygen is 2 minus, so that's 14 minus total, right? We have to hold out 2 minuses for this charge. So we only have to balance 12 minus. 12 plus for 2 chromiums mean each chromium is 6 plus. Okay? So now we've got all of our oxidation states. We can decide which one's reduction and which one's oxidation. Reduction is gain. So which one gained electrons? Chromium gained from 6 plus to 3 plus. So the reduction side is going to be this one to this one. Right? So it had to gain, well, actually, with 2 chromiums, it had to gain 6 electrons. Yeah, 12 to 6, 6 electrons. The anode is oxidation. So can't have one without the other. So this one had to go there to here. With an electron lost. Okay. Now we look at our standard reduction potentials, which are on page 29 of your review document. So these are standard reduction potentials.
This is like the crown daddy of review documents. So
Yeah, half of it's useful information. Okay, from so reduction here, this one is set up correctly for that value. So chromate to chromium 3 plus, you just have to find it. Dichromate, chromium 3 plus, there it is, about halfway down the left-hand column is 1.33 volts. Okay? Plus. This one is reversed. So we have to look at, look for this one plus an electron. Because this would be a reduction if we went from here to here. So we look at Fe3 plus. There it is, almost at the bottom, 0.77. 0.77 volts. Now that's for reduction, but this is oxidation. So this one has to be minus, and then we can't do that anymore. So this is the actual voltage for that reaction, minus 0.77. Then you just add them together. Right, so 7 from 13 is 6, 7 from 12 is 5. So we have a plus 0.56 volts.
So the, just to review, the voltage became negative because it is an oxidation, is what you said?
Yes. All those standard potentials are for reduction reactions.
Right, right.
Now, the authors, for standard potential, the authors say once you identify the cathode and the anode, the standard reduction potential is equal to the standard potential of the cathode minus the standard potential for the anode. And that's what we did. We took the standard potential for this one, took the negative of it, added it to that one, and that's what we got. I like to do it this way when there's time, because this is actually what's going on. This is just a formula that's derived from this truth. And this keeps you honest. For example, if we had two reactions and we weren't told which one was the cathode and which one was the anode, right? If we were given this reaction as plus 0.77 and this one as 1.33, then how do you decide which one's the cathode and which one's the anode? Because you're not given the this reaction to go from. This one tells you which one's which. But if you don't have that, you just have these two say, I want to make a battery. And I want to use this half reaction and that half reaction combined. Which one is the cathode? Which one's the anode? You write out your reactions as reductions. So we write this one as a reduction. And then you would look at the values. Right? They're both positive. Which one becomes negative and still gives you a positive? If you make that one negative, you got a negative value. That cell won't work. This one has to become negative, which means that's the anode. That's the cathode. Because it stays reduction. Cathode's reduction. Okay? That's why I like to write them out this way. Because then, if you're not told that information, you can figure it out anyway. The only other thing you can do is just use this formula, plug in one number here, one number there. See, oh, is that positive? No, it's negative. Flip them. That's positive. Because spontaneous reactions are positive voltages. Okay? Unlike the last chapter where spontaneous reactions were negative free energy. But for electrochemistry, positive voltage means spontaneous reaction. Okay, another.
Whatever Sarah wants to go through, I'm game. Any of it?
How about 13? This really goes to the definition of anode cathode. The anode in a voltaic cell and an electrolytic cell is, by definition, the anode is where oxidation takes place. So the anode in a voltaic cell or an electrolytic cell, remember, electrolytic is going back the other direction to a voltaic cell. Voltaic is galvanic.
Oh, those are synonymous?
Yes, voltaic, galvanic.
Is that just referring to what they're made of, or is it referring to like how they're set up? The galvanic and voltaic cells?
Actually, galvanic is probably the older term. The Italian Galvani. Well, actually, no, Volta might have been earlier. All they did was they soaked pieces of parchment in an electrolyte something that would conduct electricity. And then they stacked pieces of metal, like zinc, copper. So they have zinc, and then copper, and then zinc again. And they just stacked them all together. Then they ran a wire at the bottom. And said, what do you get over here? You get shock, you know. But they had this conductive here. So what happened was you get the electrons moving from one to the other. And if you stack them like that, that means they're in series. So the voltage of each one was additive, right? So if you made a big stack, you could get 100 volts there. You know, they used to do that at parties, you know, Renaissance parties, and it was a fun thing to do to get shocked. They had other ways of doing it. You know, they had crank generators and things like that. They had static electrical devices, these big glass globes, and you just take some rabbit fur and hold them on there, and it'd pick up that charge, and then you'd have everybody hold hands, and then one person would just touch, I mean, everybody would jump. So that was their idea of fun. Fun with science. Okay, so by definition, the anode is where oxidation takes place. That means that D is the only one that's proper. It doesn't matter if you've got the reaction going this way or that way. If you've got, say, an oxidation occurring here, then this way would be reduction. So that means the oxidation would be this way, going that way. So when you have the voltaic and the electrolytic set up this way, electrolytic is just the opposite of the voltaic. But oxidation definition, the anode is always the same definition. Right? If the anode in the voltaic cell is here, then the anode in the voltaic cell is over here. Okay. 14. All right. A strip of copper is placed in 1 molar solution of copper nitrate. And a strip of silver is placed in 1 molar solution of silver nitrate. The 2 metal strips are connected to a voltmeter by wires, and a salt bridge connects the solutions. All right, that's good. And then you're given your standard potentials for each one of those reactions. Which one is false? Okay. Sometimes, well, in my worked problems, I drew out the picture. I put it in picture form. And that can be helpful to know which is which. So if we say, let's put the information that's given. So silver plus electrons yields silver solid. So that's the metal strip of silver. And the standard potential is plus 0.80 volts. And copper produces this copper strip, if it's reduced, and then its standard potential is 0.34. Okay? If you don't want to draw the picture, all you need to do is find out which one's which. Which one's the anodes, which one's the cathode. So which one do we have to make negative to give us a positive value? That one. Right? So if we change this one to negative, that gives us a voltage of 0.46 volts. Okay, that means this one has to be written in reverse. There we go. So this one is the anode, and this one is the cathode. That's reduction, this is oxidation. Now let's look at the questions. Electrons flow in the external circuit from the copper electrode to the silver electrode. Is that true? Well, where are the electrodes being produced? The copper electrode here is giving up electrons. So they go into the circuit and cross over to silver. So that one's true. B. Let me abbreviate that. Electrons flow from copper to silver. That's true. The second one, silver electrode increases in mass. Silver electrode increase mass. Okay, is that true? In order to increase in mass, we have to add solid to the electrode, don't we? So that's what we're doing. We're making solid. We're making silver. So that one's true. There's a net general movement of silver ions through the salt bridge to the copper half cell. Let's see. Silver ions move through salt bridge. Can that happen? Well, you can't have it both ways. If the silver ions are moving through the salt bridge, then they can't be reduced here. Right? So that was false. There are ions moving, but they're not silver ions. Silver ions are being reduced right here. So they're being removed from solution. That means cations have to travel through the salt bridge from the anode to the cathode in order to replace the loss of cations. Well, we found our false one, but let's go ahead. Negative ions pass through the salt bridge from the silver half cell to the copper half cell. Let's see. Negative ions from silver to copper half cell. That's true also. Simply to maintain the charge. So what are we doing over here? We're extracting negative ions and we're dumping copper cations into solution, right? If you don't neutralize, if you don't balance those charges as they're being dumped into solution, you get a buildup of static charge. So negative ions have to travel through the salt bridge from this side to that side to balance those extra cations that we're dumping into solution. So this one's true. And the last one. Some positive copper ions pass through the salt bridge from the copper half cell to the silver half cell. Yes. Let's see, how would I say that? Okay, some copper ions through salt bridge initially, and most, well, not most, but let's just, for argument's sake, let's say the salt bridge is composed of agar with potassium chloride as our electrolyte. Initially, the potassium is going to move, but to replace it on this side, copper moves, right? So if we go far enough, we're going to start getting copper ions over here, right? Initially, potassium goes over there first, but the copper is moving also. So it's, I guess the best thing to say is it's a dynamic system. Once you connect those electrodes and make the circuit, lots of things are happening all at once.
And I'm just kind of curious, just bigger picture wise, like, when is this kind of thing used?
Salt bridge, that's when you want to connect two half cells. In other words, you can't have an electric current without a circuit, right? It has to be a complete circle. So if we're going to build a half cell over here with our copper electrode, and we're going to connect it over here with this half cell with our silver electrode, and we're going to get electrons moving this way. If we don't have a salt bridge here, then we don't have a circuit. So we need some way, some conductor of electric charge to make a complete circuit. Right. So that's what the salt bridge is for. You don't have to use a salt bridge. If you have a device set up where you can have, let's see, one cell on this side, one cell on this side, you can have a porous disc on this side with very, 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 very small pores. Just be sure that you don't get wholesale mixing between the two cells. You just have ion movement. That's a more efficient cell. Right? This provides what we call current resistance to move them through that gel. This provides less resistance. So this will give you a voltage that's closer to the theoretical. Right? And when we did this calculation, that's the theoretical maximum voltage. It's unlikely that you'll get that when you build a battery like this. Those things don't last very long. Okay. Pick another color.
From the symbol here, what's that Greek letter?
Which one are you looking at?
It looks like an E.
Oh, that's just a E, that curly E.
Yeah.
That stands for electromotive force,
Okay.
which is equal to voltage.
And but what is that? Is that a Greek letter or is it a
No.
symbol they made?
It's just an italic.
Okay.
Yeah.
19.
Okay. Okay, revert to this galvanic cell. Let's see, let me be sure I wrote that one correctly. It looks like I did. And the composition of the cell is written below it. Now that's in solution. All those components are in solution. Standard reduction potentials are given for each cell. When current is allowed to flow, which species is reduced? Okay, this is really fairly simple. 19. So I'm not going to draw that half cell. But it would be instructive to put the reactions. And the standard potential is 1.506. Okay, and this one is a standard reduction potential, 0.330. Okay. They're both written as reductions. And the way the picture is drawn, we're not told which one's which. Which one's the anode, which one's the cathode. So we have to decide which one reduces and which one's oxidized. And we just look at the standard potential. Right. So which one can we make negative and still get a positive value? To be this one. So make that one negative, then this one reverses. Now we know this one's the anode and this one's the cathode. Now we should be able to answer the question. When the current is allowed to flow, which species is reduced? Okay, this is going to be the reduction. So the manganate ion is reduced. Okay?
Can you do 20 since you already have that up there?
Which one?
20.
Oh, 20. It uses the same cells? Yeah, okay. What's the value of Q, the reaction quotient for this cell reaction? Okay, in order to do that, we have to combine the equations. And that means this one's reversed, so it has to be written this way. Okay, then we have to balance the electrons. So if this one's 6 and that one's 5, our best option is cross multiply. So we'll say this one's times 6 and this one's times 5. So we get 6 manganates plus 48 hydrogens plus 30 electrons, 6 manganese 2 plus and 24 water. Now, does that change? Nope. Doesn't change. No matter what we do to this, that standard potential still exists as is. Okay, this one becomes 10 Cr3 plus, and 5 times 7 is 35. Water, and 5 Cr2O7. And 5 times 14 is 70 hydrogens plus 30 electrons. Okay, so we're going to combine this one and this one. All right, let's see if we can cancel some stuff before we get there. Okay, waters. We got 35 waters here and 24 waters there. So these waters are gone, and 24 from 35 is 11, right? 11 waters left. The electrons cancel because that's the way we set it up. Okay, hydrogens. So this one has 70 hydrogens. This one has 48. So these 48 are gone, and 22 hydrogens left over. Okay, now we can combine it. Let's see. Let's start with this one. 6. Why am I going to all this trouble?
Which numbers, how did you choose to cross multiply with 6 and 5? I'm like kind of like.
6 and 5.
Oh, okay.
Let's see, manganate and 10, chromium 3 plus, and we got nothing left over here, but we do have 11 waters here. Okay. Now on this side, we have 6 manganese 2 plus, 5 dichromate, and what else do we have? Nothing up here. And down here we have 22 hydrogens. There we go. So let's see, can we reduce it any further? Now, there's an 11 here, there's a 5 there. These are even, those are odds. We can't reduce that any further. Okay, now, what is the Q equal to? Let me move this over because I'm going to need more board than I thought I would. So the Q expression is simply the equilibrium equation for our starting conditions, not the equilibrium conditions. All right, so we're going to have manganese 2 plus. Oops. I'll call myself a liar. Like that to the 6th power. And then dichromate to the 5th power. And hydrogen to the 22nd power. Okay. Now in the denominator, let's see. Yeah, I'm on track. I want to be sure. The manganate ion to the 6th power, and the chromium 3 plus to the 10th power, and then water doesn't count, right? Pure water is never included. Okay. So we just need to fill in the values. So manganese 2 plus, that is 0.2 to the 6th power. Dichromate is 0.3 to the 5th power. And hydrogen ions are 0.01 to the 22nd power. The manganate is 0.1 to the 6th power. Yep.
Where is that number coming from?
From right under here.
Oh.
Right. These are the beginning conditions.
Oh, right, okay.
Yep. And the chromium 3 plus is 0.4. I just left out the molar thing to the 10th power. And then you just resolve those, right? Take your powers, multiply, divide, and we should end up with 1.5 times 10 to the minus 41. So what does that tell me? That tells me that this side is very, very, very small. So the equilibrium position is primarily to this side.
Mm-hmm.
Yet, the voltage is, let's see, 6, 7, 1. Yet the voltage is 0.176 volts. Okay, so it's spontaneous this direction, but the equilibrium is over here. Seems like a contradiction, doesn't it? At least it does to me. But this tells you that the reaction is spontaneous. It will go that direction. It will go this way. It's just, it won't go very far before it reaches equilibrium. Now, is there there are 2 other pages with these on them. 22. What's the actual voltage, right? This is the standard half cell. This is the standard cell potential, right? But what are the standard conditions? This cell may not go, right? It may not give you a positive voltage. Standard conditions, what are they? Everything is 1 molar. Is everything 1 molar here? No. 25 degrees centigrade, standard temperature. Any gases in there are 1 atmosphere. But we don't have gases, so we don't have to deal with that one. Now, let's find out what the true voltage is. We've determined the Q, right? Okay, so what's the equation for the actual voltage? The Nernst equation. Actually, the modified Nernst equation, which takes into account the fact that we're at 25 degrees centigrade, and we're using common log rather than natural log. Those conversions have already been made in this formula. Okay? So, we know this one because we calculated it right here. We know this one because we calculated this part of it. What's this one? That one is how many electrons were transferred. Right. So we have to look back up here. This doesn't have the electrons, but this one does, and there were 30 of them. Right? So this value is 0.176. Then we have 0.0591 over 30 electrons. And then we can take the common log of this value.
Where is the 0.0591 from? Where was that?
We did that in class. It's also useful information. Should be. Let's check to be sure. In that table. There we go. On page 28. It's at the bottom of the page. In the middle. Okay. This is the modified Nernst equation. The unmodified Nernst equation has several factors in here, plus natural log there. And if we were chemical engineers, we'd have to use that one, right? Because temperatures vary and other factors vary. But in most cases, we've made the adjustments for all those other terms and the log and buried it in that constant at 25 degrees. Okay? Look in the PowerPoints. I think I've got a slide in there where we derive this one. Okay, so you can see what
And so N is the number
of moles of electrons that are transferred in the reaction.
Number of moles of electrons that are transferred.
Right. For that, you need to actually do the redox balancing. And the step right before you combine them into the final equation, that step gives you how many electrons were transferred. And then, if we did our math right, it should be 0.2 something.
That final, so you don't look at the final equation, you look at the
Say again. This one?
right, you didn't look at that, it was the one right before it where you were canceling out stuff.
Right.
And adding them.
Right. We had multiplied each one to make sure that the electrons balance. So when we combine this one with this one, 30 electrons here, 30 electrons there have been transferred. Went from here to here. That's the value of N. So the reaction is spontaneous, even though the equilibrium lies over here. Let's see where we do that. The Nernst equation is middle right-hand slide on page 9. of your PowerPoints. So that 0.59 incorporates transitioning from natural log to common log, the temperature, the universal gas constant, and Faraday constant. They're all buried in that 0.591. This is the one you're ever going to need anyway.
So that's the Nernst equation now, right there, E equals.
I call it, huh?
How would you read that correctly?
The actual voltage is equal to the standard voltage minus 0.591 divided by the number of electrons transferred times the common log of Q for your reaction. I'll leave that up there for a few more minutes. Oh, he's on his way. 8:31. He must have taken the southern route.
And so in writing the value for voltage, we don't have to do scientific notation. We just can do 0.26.
Yes. Yeah, that's fine.
I think I need
A break? Okay.
just for 1 minute. Stand up, get some oxygen and maybe coffee.
Full password. Okay, processing done. Good. Now I need to go into Blackboard. Wait. Right back.
How does this sound? I'm not sure.
Zoom.
I'm the hospital with the somebody in the extra doing and so
Was Jimmy able to make it in last week, Dr. Black?
I think so.
Yeah, sorry I wasn't able to come in. I had to make the choice for myself that day, which was not driving over here.
Mm-hmm.
So was that lecture able to upload?
Yeah,
Okay, great.
it's I'm putting it in the Blackboard now. Just a hey. There. didn't pause that. Be a lot of dead air in this one. Okay. Okay. A little less than an hour left if we need it. Another one?
31.
31. Okay. This one should be fairly straightforward. What's the standard cell potential for the following electrochemical equation? So we have 2 lithium, copper, copper solid. Okay, for this one, since it's standard potential, all you need to do is decide which one's the cathode and which one's the anode.
How does one decide that?
You look at the oxidation states. So copper's 2+, lithium's 1+. Those are given because they're single atoms with charges. So their oxidation states are there. And then the elementals are always 0 in their standard states. So we're given already. I mean, that's easy. So what happens to lithium? It goes from 0 to +1. It lost an electron. So 2 lithiums lost electrons. And just to balance it, do that. Cathode then would be the other one. So copper had to gain electrons. Okay, now what are the potentials? Where am I? So the standard potential for this one is minus 3.04 volts. That's the reduction potential. Okay. That's the way it's given. And the one for this one is 0.342 volts. Okay. If we, well, the reaction tells us which way is which. Right? So this one's oxidation. That means this one has to be changed to plus. Okay? So now we have to add them together. So that's 6. Actually, is that right? Yeah, it sticks out. 2, 4 and 4 is 8, and 3, 3. Okay?
Okay, cathode is reduction, anode is oxidation.
Right.
I just have to say it with my own voice many times and it'll stick.
Yes. Reduction, oxidation.
So why is an elemental solid lithium is just 0?
Oh,
Why is that?
all standard state elements have an oxidation state of 0. So if they're metals, they're going to be solids, except for one.
Oh, so that S, I thought then that S stand for solid.
Yes, right, that's solid.
Okay.
Mercury is the only one that is standard state liquid.
Okay.
And then for the nonmetals, it can vary. Standard state for hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, they're all I2. But these are gases. That's a liquid, and that's a solid at 25 degrees centigrade.
And at that state, they're all, you said, zero.
Oxidation state. Yes.
So just for my own, the sake of my sanity for this exam, will we probably deal with things that I would know that, or like you won't throw in something like bromine that's liquid in its state?
Actually, it wouldn't matter.
It wouldn't matter.
No. The only thing you're concerned with in most cases is to know which ones are diatomic. Because standard state for these, hydrogen and these guys, are all diatomic.
For hydrogen, fluorine, or sorry, nitrogen, oxygen, fluorine, chlorine, bromine, iodine.
They're all subscript 2. They're diatomics.
And don't let that throw me off. They're still a zero.
Yes.
Okay.
Okay. I think that was 31, wasn't it? How about the shorthand notation? Uh, 33, we encounter shorthand notation. So this is a shorthand description of the galvanic cell. Calcium, vertical line. What does that vertical single line mean? The phase difference. This is a different phase than what's next to it. Right? So this is going to be, we know that's going to be a solid. This is going to be an aqueous solution, so obviously there's a phase difference. Then what's this mean? Right, that's a divider. It's like a salt bridge or a porous disc or something. Then next we have this, then a phase difference, and that. So what's happening? Well, the convention is we're going from this 0 state to that 2+ state. So this is the oxidation side of the anode. Going from here to here. Over this side, we're going from here to here. Reduction. We have to add electrons to here to get that. So this is the cathode. So by convention, the shorthand notation puts the anode on the left, cathode on the right. No matter how you draw that those little pictures I put in here. Right? This is convention for shorthand notation. And if you have the information, you put in the concentrations if you have it. So we would put in the molarity of this one, the molarity of that one. And of course, these guys are going to be solid, so that doesn't matter. Or if you have anything that's in here gas, you would put in its partial pressure.
And so the concentration is what you're saying.
Right.
Molarity.
Let's see. Which of the following statements is true? Oh, okay, so the half cell on this side, the standard potential is minus 2.87 volts. And the standard potential for this cell is minus 2.93 volts. This is the oxidation state side. So its potential is going to be plus. Right? We have to reverse because this is oxidation, standard potential is always reduction. So if we add those together, is that cell going to be spontaneous? As written? Nope. Because you add them together, you get a negative number. So A, the cell reaction is spontaneous with a standard cell potential of 0.06 volts. In reality, the standard cell potential is minus 0.06 volts, as written. So this one is false. The cell reaction is non-spontaneous with a standard cell potential of minus 5.8. Well, it is non-spontaneous, but it has a voltage of 0.06 volts, negative 0.06 volts. So B is false because the value of E is wrong. All they did was they took this negative and added that negative together. You can't do that. The cell reaction is non-spontaneous, true, with a standard cell potential of minus 0.06. Yep, that's correct. Non-spontaneous, it has this voltage. Now, which way would it be spontaneous? When you hook that cell up, which way is it going to go? It's actually going to go that way. It's going to go backwards to the way we've got it written. So if you want to write the spontaneous cell, you would put this over here, actually with that one over here. Let's do it.
And what is,
Yeah, go ahead.
is telling us that it is spontaneous or non-spontaneous again?
The sign.
The overall voltage under standard conditions
Right.
is negative.
That's non-spontaneous. Now the key there is standard conditions. If the conditions are not standard, if we have, this would be 1 molar, that'd be 1 molar. If these are different, then we could actually write it this way and produce a spontaneous reaction by adjusting the concentrations here. Okay, using the Nernst equation, we find out what the true voltage is. If that's positive, then this could be spontaneous, but they would be non-standard conditions. But under standard conditions, to make this spontaneous, we would have to write it like this. And then put this one over here. That would be spontaneous under standard conditions. Well, let's see. D, the cell reaction is spontaneous. No, it's not spontaneous. And E, the cell is at equilibrium. Is the cell at equilibrium? Well, under standard conditions, we do have a voltage. I mean, it might be negative this way, but the only time the cell is at equilibrium is when the voltage is 0. Now we could adjust the concentrations in such a way that the actual voltage would be 0. If that were the case, then the cell would be at equilibrium. If the actual voltage is 0. That turned into more than I expected.
Sorry.
That's all right. It's good. Teaching moments. They're always allowed.
I think I've consistently thrown off your timing for lectures by asking questions.
Keep me on my toes.
Well, then it's a win-win.
Yeah. Let's see.
I'll keep you on yours and you can just show me where mine are.
Let's see here. Any others while I'm perusing?
36.
36.
Oh, boy.
Consider the following reduction potentials for a galvanic cell employing copper and lead. Calculate the maximum amount of work that would accompany the reaction of 1 mole of lead under standard conditions. Maximum amount of work. Okay. So, let's see, do we need to know? We need to know what the voltage is, yes, because the maximum amount of work is related to this formula. The maximum amount of work is how much charge is transferred at the maximum voltage. So we got to know two things.
So that little Q.
Little q is charge, right? In this case, okay, sorry. For electrochemistry, Q is charge. For thermochemistry, Q is heat.
So the amount of charge.
Right. And this is charge in coulombs. So we've got to make a conversion on the number of electrons transferred converted into coulombs for 1 mole of lead. So we've got to identify our cathode and our anode.
Let's see.
Okay. Let's do this. Let's put our reactions up there because we don't know which is which yet. So this is going to be the standard reduction of copper to copper metal, copper 2+ to copper metal. And the standard potential is 342. And this one is the standard reduction potential for lead. Right. So its standard value is minus 0.130 or minus 0.130 volts. Okay, now we got to decide which one's cathode and which one's anode. Right, which one do we, if we make this one negative, the anode, we get a negative number, it's non-spontaneous. Right, so we have to change this one. Right, so this one's going to be positive, and then we have to write it this way.
Why do we want it written in so that it is spontaneous? What's that effect?
Well, that's so it'll be a battery. You can't get any work out of a non-battery,
Okay.
right? And it has to be spontaneous, we can't get work out of it.
Okay.
Okay. So the voltage then for this cell is going to be this one plus that one, which is 0.472 volts.
So you always have to change the sign of one of them?
Yep. If they're given to you as reduction potentials, you can't put those two together as both reductions. One of them has to be oxidation.
Okay. Yeah. So one of the signs has to change, and it has
Correct.
to keep the number positive.
Right.
Okay. Gotcha.
Okay, now we have our voltage. So here's our Emax voltage, right? And now we need to find out with 1 mole of lead, what charge does that represent? This is dimensional analysis. So 1 mole of lead what's the relationship? 1 mole of lead here, 1 mole, is related to 2 moles of electrons. That's the ratio, 1 to 2, 1 to 2. Okay, so we got 2 moles of electrons, but that's not coulombs. How many moles of electrons are equal to a coulomb? 96,485 coulombs. That should be in useful information. Let me check just to be sure. On page 28. Let's see, there it is. Second column from the left, about 2/3 of the way down. This is called the Faraday. 96,485 coulombs per mole of electron. This whole thing here is equal to the Faraday constant. Okay?
Which column is it again?
Second column from the left, about 2/3 of the way down.
I found it.
Yeah. So then this value becomes, so I don't have to use my calculator.
So you can use
Becomes
that for conversions, is what we're doing, you're converting
converting 1 mole of lead into coulomb of charge.
into coulomb charge.
So if we convert 1 mole of lead into lead 2+ ions, that represents 1.9297 times 10 to the 5th coulombs of charge. That's what that conversion means. Then find the maximum work. We'll take this value for our Q with a negative sign. 1.9297 times 10 to the 5th coulombs times the Emax, which is 0.472 volts. Okay. If you're concerned about units of measure, proper canceling, right? Work is what? Work is energy. It's going to be in joules, right? So in order to get joules out of this, we need an equivalent value for volts. And the equivalent to volts is joules per coulomb. They're equivalent. So now the coulombs cancel and leaves us with joules. And let's see.
So volts is like joules per,
It's not like, it's actually equal to.
is equal to
Yes.
per coulombs.
And the 4th joules. And none of the answers match that, so you have to convert it to kilojoules.
And our Q, so charges in coulombs.
So that's the maximum amount of work you can get from this cell when 1 mole of lead is converted to lead ions.
And that's just based on, so if instead of having copper in there, this could potentially have a different answer based on the lead circulating with the electrons with something else.
Yes, if you had a different half cell here,
Yeah.
it would give you a different voltage.
Okay.
which would substitute in here and change the amount of work. Yep. It's kind of like, I like to think of it as, in order for a spontaneous reaction to occur, you're going from this level to this level. That's your voltage. And electrons are moving down.
So what are some good pairings? Like, I'm sure that they've run all these tests already. I'm just.
Oh, yeah. All we have to do is look at the standard reduction potentials on page 29. What would be the maximum voltage we could get from this page? If you paired a cell that was composed of fluorine,
So could you combine any of these together, or
theoretically,
just are
there may be some engineering problems involved, but
So these ones that are like lithium that has a negative 3.05.
right. And if we take lithium, lithium is negative. The reduction of lithium is negative. So in order to make it work with this cell,
With fluorine.
we'd have to
make it the, don't say it, dummy say it, make it the cathode.
no, this is the cathode.
Make it, sorry. The,
Reduction.
Make it
Make it the anode.
anode.
In that case, we would say lithium then yields lithium plus electrons. Then our voltage would be 5.92 volts. For this table, and this is not an exhaustive table.
Right, but just for our purposes here, for me understanding.
Right. If you couple fluorine with lithium,
That's probably at the highest voltage we'll get.
that's the maximum voltage you can get from that cell, using those two half cells.
So once you make your battery with this 5.92 volts, I mean, then how do you get the work out of it? What do we do then?
Oh, you have a half cell here, a half cell here. This is your anode. This is your cathode, and this is true for any cell. So you have your salt bridge. Then you have your cell here. And you connect it externally, so your electrons are moving that direction. And then you put something in here, say a little motor. And the movement of those electrons through that motor generates motion. You can take that motion and do work with it. Or you can couple it with some other reaction and drive that reaction backwards. As long as this voltage is higher than that one, you can get work out of it. Or,
And that's just spontaneously happening.
yeah, until it reaches equilibrium. When it reaches equilibrium, then it stops. That's otherwise known as a dead battery.
So what's the life on this then? Like how long would it last? If you set that up just like that with the fluorine and lithium, then how long would it go until it reached equilibrium?
You can calculate it, but it depends on, this voltage is standard state. So let's see, fluorine would be gas, so it'd be 1 atmosphere. Lithium is metal, so this would be 1 molar. Right. Under those conditions, you could calculate how long it would last.
Really?
But the way to make a cell last longer is to produce the largest Q possible, maximum Q.
But and for the saltwater bridges, like you said there was another option. It was either a saltwater bridge or
Oh, a salt bridge or a porous disc.
porous. So any salt works there, or are there ones that are?
No, you can use anything soluble.
Chloride.
Yeah, potassium chloride is common. Yeah. I've used others, potassium sulfate. Sulfate ion is pretty big, so it kind of puts up more resistance in movement.
So
And-
a kind of lightweight salt.
Yeah, you generally pack this with a gel to keep the general mixing from going on, but let the ions move. Some, they have the liquid in here, and they just have a gel plug at the end. That makes it even more efficient.
What's the
The gel auger. Yeah. Have you had micro? You know about auger plates? Those little Petri plates, and they have auger in them. It's a gelatinous substance made from seaweed, and it produces a non-flowing colloid. Right. Jello's a similar to auger, but Jello is made from cow bones. And it's a protein. I've used it in this method.
Really?
Yeah,
Oh.
but it presents a problem
Why?
because proteins have their own electrochemical potential.
Oh.
So you think you're going to get a certain voltage out of your cell, and the salt bridge introduces its own voltage. Yeah, auger doesn't do that. So, but auger's not typically available. I was able to get, gelatin off the grocery shelf.
I mean, who gets this idea? Like, let's get this gelatinous substance of seaweed and use it here in this application, and yeah, it works great.
I don't know.
Who thinks of that stuff?
Some of this I just inherited. Like most chemistry, I inherited it. It's been accumulating over many decades.
I know this is not going over a review question, but this kind of information helps me synergize all of it.
Oh yeah.
Bring it, and I need that to put it together.
I sympathize. I do the same thing. It's just that I've already done it, so I don't think about it when I'm teaching it.
Right.
So it helps me to be diverted.
Sorry, not sorry.
Okay, anything else? Let's see.
So with our lab, which I haven't read through yet, what time's the lab start?
10:30?
Well, I don't want to detract from any more review questions being gone over. So Sarah, do you have some that are running for you?
About the only thing left is running a reaction in reverse, making an electrolytic cell, and
when
things
you
like-
say electrolytic, that really is this referring to taking it back the other
back the other way. Yeah. So if you run it in reverse, rather than plating metal out on this side at the cathode, you run it in reverse and put the cathode on this side and plate out the metal over here. Example, chrome plating bumpers. They used to, because they're not common now, on antique cars, yes.
Mhm.
So you would take your bumper, which has already been plated with copper and nickel because chrome will adhere to steel. But then you submerge your bumper in a chromium solution, chromium 3+ ions probably. And then you run current in reverse, and you cause the chromium to be reduced and deposited on the bumper. And you can tell with a certain voltage and with a certain time, voltage and current, I should say, current and time, you can tell how much chromium metal you can deposit on that bumper in that amount of time. We have a problem in here like that. Let's see.
Howdy.
How's it going?
Does your copy look like this one?
Yeah.
Well, there you go. I'm gonna be sure you've got those I was straight out of my head. Yeah, that was giving you the wrong copy, so side by side. Yes, we're good. Okay. Electrolysis. So let's see, let me get an example here. How about
This seems very involved. Is this due next Monday as well?
this lab?
Hmm.
Yeah, because that's our exam, our last exam. Isn't that finals week?
Yeah.
May 6th.
Okay, for instance, 60 looks like a candidate. Let's try that one. All right. An electrolysis plant operates its electrolytic cells as a total current of 1.8 times 10 to the 6th amps. So current is given an I. This is physics.
Other favors.
10 to the 6th amps. Okay, how long will it take to produce 1 metric ton of magnesium? So the mass of magnesium is going to be 1,000 kilograms. That's a metric ton. Okay? Oh, we're given here 1 million grams. Okay. So times 10 to the 6th grams. There we go. From seawater containing magnesium 2+. So what's going to happen? Well, if we're going to produce magnesium metal, we have to reduce the magnesium to magnesium metal, and that will take 2 moles of electrons for every mole of magnesium, right? Because you have to balance those charges to make this soluble. Okay, so this is actually a unit conversion, dimensional analysis problem. So we're starting with this one. This many grams of magnesium. Right? So how many moles of magnesium do we have? Because we have to find out, in order to know, what's the question?
How long will it take to
How long?
produce 1 metric ton?
Time. Time is the question. How long will it take to produce 1 metric ton? So we've got to convert this into that because this contains our time factor. This is an amp is equal to 10 to the 6th coulombs per second.
So amps are coulombs per second?
Mm-hmm.
Ugh.
Yep. Okay. So we've got this many grams we need to find out how many moles so we can find out how many electrons, because we can't get to this without our electrons, because that's current. So here we need grams of magnesium to moles of magnesium. And that's 24.3, isn't it? Yeah, 24.3 here. So this gives us moles of magnesium. Now we want to find out how many electrons. What's the ratio? 1 mole of magnesium for every 2 electrons. So 2 electrons for 1 magnesium.
Why did it change from? I'm sorry, it didn't change. I just misread your number up there. Okay. You just rewrote it. Okay.
Yeah. Mm-hmm. So that one's gone, that one's gone. Now we have 2 moles of electrons. We have electrons as our unit. And at this point, let's find out what that value is. That's how many moles of electrons have to be transferred in order to produce 1 metric ton of magnesium. That many electrons.
Is that what your N is up there? That's a metric ton of magnesium.
Yes, mass of magnesium.
Okay.
So now we know how many electrons have to be transferred. Okay, hold that thought. Let's find out how many electrons. What's the question? Again, it just says how long, right? I'm going to convert this to electrons per hour. So that means I've got to go 1.8 times 10 to the 6th coulombs per second, right? And we need our Faraday constant to convert to moles of electrons. 485 moles of electrons per coulomb. Oops, that's not right. No, it's the other way around. Coulombs per electron. Coulombs per mole of electrons. There we go. So that gets rid of coulombs. Moles of electron per second. Now I want this per hour. The only reason being that if I don't, then we're going to end up with seconds. And the answer, well, there are no seconds in the answer. The answer is either hours, days, minutes, or years, right? So we know we're not going to need seconds. Let's just change it to hours. Then we can make easy conversions if we need to from there. So how many seconds in an hour?
36.
3,600. Right? Okay. So now this becomes 6.716 times 10 to the 4th moles of electron per hour. That's what this represents, the current. The flow of electrons in 1 hour. That's how many in 1 hour. And this is how many moles of electrons are transferred. So if we take this one and use that conversion, moles of electrons on the bottom and hours on the top, will give us how long it takes. And I rounded off to 1.2 hours.
So I'm looking at the review guide. So the first thing you did was converted 1 metric ton of magnesium into how many moles of electrons
Right.
it would be.
Mm-hmm.
So you got that number, and then you took and converted amps into moles of electrons per hour.
Yeah. We're sort of merging these two together. and we put them together over here.
And then calculate it, and then multiply those to find out how many hours.
Yeah, I actually divided that one by this one.
Right, divided, but it was set up like,
Multiply the inverse.
right.
And that turns out to be one of the answers. 1.2 hours. It would take that long at this current from seawater to produce 1 metric ton of magnesium.
So this question required that you understand that coulombs per seconds is amps,
Yes.
that time is buried in there. So knowing how to approach the facts at hand.
Right. That's the tricky part right there for most students,
Right.
especially if you haven't had any physics and you don't know that.
Oh, it's been since high school.
I didn't even have it in high
I
school.
had it in high school.
In that case, if you need to know that on the test, just ask me. Right? If you say,
What
if
would
you see,
be the proper question, like?
oh, if you see amps there,
Yeah.
what does amps
What
mean?
are amps exactly?
Right.
It's
What
funny. because
Relatable terms have we talked about that I don't know what to do with?
I'm trying to imagine 1,800,000 amps because I've heard that 2 amps is enough to kill you.
Mm-hmm. Yeah,
What is the I?
this is current.
Shouldn't be a C.
Uh-huh.
So why?
Not physics.
Oh,
I is current physics.
oh my gosh. Can't you all get on the same page?
No. Scientists agree on some things, but other things they have their own little bailiwicks.
Sounds about right.
We talk our language so nobody else will understand what we're saying.
Really, it's simple one half dozen of the other.
When I finished my master's degree in food science, I went to work in the agronomy department on the LSU campus.
What's agronomy again?
Agronomy, crops and soils.
Okay.
And it took me a year before I felt comfortable with their lingo, because I heard all these terms flying around. They didn't make any sense. But eventually, you know.
And that was postgraduate degree.
Yeah.
Yeah.
Well, I worked for them for a year before I decided I wanted to work on a PhD in that subject. So I wasn't taking any classes at that time. And then when I did go back, start taking classes toward a PhD, like an idiot. First class I took was physical chemistry.
Physical chemistry.
It's the physics of chemistry. It's very mathematical.
It's right up
Makes me sad.
my alley.
And you don't realize how rusty you can get in just 1 year off.
Oh,
Well, maybe you do realize.
yeah.
I realized with Joyce even she was like, yeah, there'll be a lot of concepts that you should remember from Anatomy and Physiology 1 that you just had last semester. And I was like, oh, I had it 3 years ago.
Mm-hmm.
Didn't remember much of anything. I remember the bones and the muscles and the structures of the cell because I learned that in high school anyway.
Yeah.
The oh God, okay, I don't know what the system is. The hormone system.
Endocrine?
Yeah,
Endocrine.
the endocrine system. That was one of the last topics covered, and it was called back on a lot. And I had nothing.
Well, let's see.
Are we doing the?
We didn't do any balancing redox reactions for basic solutions. How to do that. It's really simple. Use what I call the false acid method. So remember, we balanced by, we divided into reduction, oxidation steps, and then you balance the non-oxygen hydrogen first, then you balance the oxygen with water, and then you balance the waters with hydrogens. Right? Then you add in your electrons where they go, then you balance the electrons between the two before you put them back together. And then when you put them back together, that reaction is going to be an acidic solution. You're going to have protons. So how do you make it basic? You just take hydroxyls, add enough hydroxyls to cancel all of the protons, because they're going to be on one side. And then those hydroxyls, the same number of hydroxyls, you put it on the other side too. So when you balance those hydrogens on this side with hydroxyls, what do you get? Water.
Whoa.
And if you have water on this side and water on the other side, then you have to balance those two. So cancel from both sides. And then on this side, you'll have hydroxyls, and that's your basic solution. So once you get the acid balanced, then you do that conversion for hydroxyls, and you got basic solution.
And this was in reference to one of our questions?
Yeah, there's several examples in there. I mean, we can do one.
Yeah, let's do one. Because you were just pointing at an imaginary equation up there.
Okay.
I was, getting a kick out of it, but I thought, maybe some actual.
You have to have a very vivid imagination for this discussion.
Just walk with me on a journey, students.
Okay, let's see, where's a good example? I'm looking for basic solution balancing. Let's see here. Oh, first page. Number 4. Okay, the following reaction occurs in basic solution. There's our fluorine. They actually put water in already. Oxygen and chloride ion. So now we have to decide which one's reduction, which one's oxidation. Elements, remember? 0, 0.
Well,
Minus 1.
Fluoride is reduced.
Fluoride's reduced. So reduction would be this one. Yields this one. Oxidation then would be
H2O.
H2O.
Yeah, H plus.
And then O2. So the oxygen is the one that changes.
I'm assuming it's okay that equation's not stoichiometrically sound.
No, we're supposed to balance it.
Oh, okay.
Right, this is just a starting point. So, non-oxygen hydrogen balance here, there's nothing to deal with. Here, we need 2 of these. Okay?
Why is that? Back to the water? Why did she say that?
Oh, because the procedure says that first thing you do is balance the non-oxygen, non-hydrogen elements.
Okay.
Since there are none here, we don't have to deal with it. But for this one, we have 2 fluorines here, we need 2 on this side. That's your first step. Second step is balance oxygens. Well, we've got an oxygen here and 2 there, so we need 2 here. We don't have to add water to this one because it's already there. But we do need to add hydrogens to balance the 4 that are on this side. There you go. Okay? Now we've balanced oxygens, balanced elements, oxygens, hydrogens. Now we can do electrons. So this one is your reduction. That means we have to add electrons on this side. How many, actually? Well, we're going from 0 to -1, so that's 1 electron per fluorine. So we need 2. This one is going from 2 minus to 0. That means it's oxidized, and electrons go on the right side as a product for oxidation. But how many were transferred? Well, for each oxygen, we went from 2 minus to 0, which is 2 electrons. But we've got 2 oxygens. So that means 4 electrons total.
So it's just understood that the oxygen is 2 minus and the H is plus 1.
Yes. Okay.
So 4 electrons.
Oh wait, no, I guess H2 wouldn't be positive, would it?
Yeah, it's 1 plus.
So the oxygen.
2 times 1 plus balances 2 minus.
Oxygen's 2 minus.
Uh-huh.
So we're only.
Those rules are in your PowerPoints too. Now, we can't put these back together until we balance the electrons. This one has 4, that one has 2. We have to multiply this one by 2. So there's 2, 4, and 4. So we're going to add that one to this one.
Let's see. So
2 fluorines. Electrons cancel. Just throw those out. And 2 water yields.
So all you wanted to do is make the electrons balance. So back up
Yeah.
1 step. So we balanced the oxygens, and then we had our electron count 4, but there was only 2 up with the fluorine, and that's the next step, balance the
Right.
electrons.
Right.
So now you're multiplying the whole thing through by 2 for the fluorine, and that's only so that the electrons balanced.
Correct.
So now we have 2 F2, 4 electrons, and 4 fluorine.
Right.
And now you're going to combine those 2 things.
Now you can combine. Yes. Okay.
Okay.
Now, that's acidic solution. Now we're going to convert it to basic. So we got to neutralize the acid. Right? That means on this side, we have also 4 hydroxyls. We added them over there, we got to add them on this side. So this is water, 4 waters. We got 2 waters over here, so those 2 cancel, leaves us with 2. So our balanced equation is 2 F2s plus 4 hydroxyls yields 4 F minus plus O2 plus 2 water. Oh, the question is, what's the sum of the coefficients? All right. So 2, 6, 10, 11, 13. The sum of the coefficients is 13.
Okay, so
And you crossed that 2H2O because.
Because we have 4 on this side.
the
Okay.
4. Oh, I didn't write these. 4. Yeah. So the 4 electrons cancel out. I'm still back there.
Mm-hmm.
And so we end up with 2 F2 plus 2 HO, 2 H2Os
Uh-huh.
yields 4 fluorines, 2 oxygens, 4 hydrogens.
Mm-hmm.
And then you said so that this was the acidic solution.
Mm-hmm.
But then all you did to balance it out was added 4 hydroxyls to both sides. Right?
Right.
And that,
Converted this to water. 4 waters from this reaction. And then these are by themselves. Then you have to deal with the water being on both sides. So you have 2 waters here, 4 waters there. If you subtract 2 waters from the entire equation, gets rid of this one, gets rid of 2 of these.
I ran out of space to write the rest of it. Let me see if it's on your pages. Do I need to write it all?
Should be. Number 4.
Let's see.
Yep, step by step.
So
How long does this lab take?
Probably take the whole time. So we'll have to make the salt bridge. That means you got to boil water. You got to dissolve the agar. You have to transfer the agar into the U-tubes. Let it solidify. While that's going on, set up your half cells with your copper and zinc.
oh goodness. Okay.
Oh, I gotta get the multimeter so you can measure the voltage. It's in my office.